Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome to the Deep Dive, the show where we take complex technical materials and build you a mental map so you can walk away well-informed, fast.
Today, we are wading into the intensely complex world of industrial microbial fermentation. And this isn't just, mixing things in a big steel pot.
Right.
This is an adaptive biological process happening inside these highly engineered vessels that we expect them to behave predictably at scale.
And our sources for this really lay out just how intense the requirements are for modern biomanufacturing. It's no longer enough to just record what happened for, say, compliance or a report.
No, not at all.
The analytics, the tools that tell us what the cells are doing, they now have to be the core engineering infrastructure. They have to be integrated into every single part of the process.
So our mission for this deep dive is to understand how Process Analytical Technology, or PANET, combined with really rigorous data integrity, creates the nervous system of a modern fermenter.
A nervous system, I like that.
It's the mechanism that translates raw physical measurements, temperature, pressure, that kind of thing, into actionable biological insights about cellular health and metabolism.
So the ultimate goal here is to focus on this fundamental shift that's happening, how analytics are moving from just being simple monitoring tools.
Right, things that just report a result after the fact.
To powerful, real-time decision enablers that can actually anticipate and prevent yield loss.
Exactly. The paradigm has completely shifted from, let's say, post-mortem investigation to real-time process steering.
Okay, let's unpack that idea of analytics as a decision enabler. It sounds great on paper, but what did the sources emphasize that really contrasts with that older role of just being an auxiliary recorder?
Well, what's really fascinating here is how analytics bridge the gap between two very different worlds, engineering and biology.
Okay.
The engineering side, it deals with measurable physical signals, the precise flow rate of gas, the jacket temperature, the pressure. But the biology side is worried about completely different things.
Like the cell's metabolic state, their stress levels, that sort of thing.
Exactly, their growth efficiency. The analytics are the translators that turn those physical measurements into a picture of biological reality.
And the primary translation tool, which is also really the only continuous outflow measurement you have in these huge fermentations, is off-gas analysis, right?
That's absolutely the backbone. By measuring the KO and O levels in the exhaust, we can continuously estimate two key variables: the oxygen uptake rate, or OR,
Okay, OR.
and the carbon dioxide evolution rate, CER. And these readings aren't just technical numbers, they're real-time indicators of how fast the cells are breathing and processing the carbon source we feed them.
And this leads us directly to that crucial metric they derive from the data, the respiratory quotient.
The RQ. Yes, the RQ, which is simply the ratio of CER over OR.
And why is that ratio so fundamentally important to managing fermentation?
Because a rising RQ at a constant controlled feed rate is a critical early warning sign. It's a red flag that failure is coming.
How so?
Well, if the RQ climbs above, say, 1.0, it means the rate of co-evolution is higher than the rate of O-year consumption. Biologically, that's the fingerprint of inefficient energy dumping.
Meaning the cells have too much food but not enough oxygen to process it properly.
Precisely. They have excess carbon, usually glucose, but they're limited by oxygen. So they're forced to shed that excess burden by producing acidic byproducts, like acetate and E. coli, which basically poisons the culture.
So if you see that RQ spike, you know you're about to lose yield before the biomass or your product concentration even starts to visibly drop. That's impressive.
It is.
And it leads right into this concept of soft sensors. How do soft sensors use these simple measurements to estimate the really critical but often unmeasured variable?
Soft sensors use these advanced modeling frameworks, often built on mass balances, that take easily measured, reliable variables like off-gas data, feed flow, and pH.
The things you can trust.
The things you can trust. And they dynamically estimate the hard-to-measure stuff, like true viable biomass or the specific growth rate, MO.
But if we're using models to estimate something as critical as biomass, aren't we just swapping hardware uncertainty for modeling uncertainty? I mean, what happens when the model breaks down in a really stressed batch?
That's a really valid concern, and it's why industrial adoption requires so much validation. The sources show that by explicitly modeling and accounting for measurement error propagation.
Meaning you quantify how the error in one reading affects the final estimate.
Exactly, you track the uncertainty. And by doing that, these soft sensors can actually provide significantly tighter feed control than relying just on sporadic manual offline sampling. You get around the time lag and the sample variability.
It's a necessary compromise then. The speed of the soft sensor outweighs that occasional uncertainty. Okay, so moving into the tools themselves. The sources call online continuous tools the backbone of PATE. Beyond off-gas, what's another critical online tool?
Capacitance, or dielectric measurement, is crucial for tracking viable cell concentration.
And that's different from just measuring how cloudy the broth is, right?
Yeah. Very different. Unlike turbidity or optical density, which measures everything, live cells, dead cells, aggregates, capacitance, works by applying an electrical field.
And what's it actually measuring in that field?
It measures the electrical property of the cell membrane. See, live, intact cell membranes store charge like tiny capacitors, so it can specifically distinguish the volume of viable cell mass from all the other junk in a stirred fermenter.
But there's always a catch, isn't there? Especially in the real world. What stops capacitance from being the perfect solution?
Its accuracy really degrades under some common industrial conditions. For one, at very high cell densities, the signal just saturates.
Okay.
Second, strong foaming interferes dramatically with the reading. And crucially, if the cell morphology changes, like if a yeast switches from budding to filamentous growth, the calibration often becomes invalid.
So when that signal degrades, you have to pivot to at-line tools, things like HPLC or enzymatic assays. They give you higher specificity, sure, but they introduce a huge risk, time lag.
The time lag is the critical factor. The sources cited this powerful real-world example in commercial enzyme fermentations, where delayed substrate measurements combined with control algorithms that were too aggressive.
They led to what they called oscillatory feeding.
Exactly. The system was just constantly overcorrecting.
So the culture was bouncing between being fed too much and then being starved.
Precisely. It was constantly cycling, fed too much substrate, which leads to toxic excess, then immediately starved. This just ramps up metabolic stress and increases byproduct formation. The data was arriving too late to be useful.
That has to be a cruel irony. You build this whole analytic system, but the delay is the very thing crippling your yield.
And that's where soft sensors came in again. They helped infer the cell's actual uptake rate and limited the feed based on the cell's real demand, which stabilized productivity.
Okay, let's tackle what sounds like the most insidious challenge of all. Sensor representativeness. We can have a perfectly calibrated sensor, but if it's in the wrong spot, the reading can just, well, lie to us.
This is such a critical point in large fermenters, and it's all driven by spatial heterogeneity. Gradients. Mixing limitations in these massive tanks create gradients in everything. Dissolved oxygen, substrate, pH. A single-point measurement often does not reflect the average environment the cells are actually in.
Can you give us that specific scenario they used to illustrate this false security risk?
The oxygen example is perfect. You might have a DO probe placed conveniently near the impeller or the sparger while the oxygen is being pumped in. It reports acceptable, safe DO levels.
It's good on a screen.
Looks great. But because of vertical oxygen transfer limitations, regions far away from that probe, maybe near the bottom of the tank, could be experiencing repeated severe oxygen limitation. It's called DO cycling.
And this isn't just about oxygen running low. It's about a race happening inside the tank itself.
It is a hydrodynamic race. In large tanks, the time it takes for a cell to cycle from those oxygen-poor zones back to the oxygen-rich zone is often slower than the cell's maximum oxygen consumption rate.
So the cells are repeatedly suffocating and then being revived.
And that forces them into anaerobic metabolism over and over, killing productivity. Even when the average DO reading looks perfectly fine, the problem is exposure to the gradient, not the average reading.
So your single probe is telling you everything's fine while most of your culture is suffocating. What are the engineering solutions to fight that?
Well, it starts with redundant measurement. You install multiple DO probes at different heights and locations to actually detect and quantify those gradients.
You map it out.
And then you combine those hard sensors with global soft sensor estimates from the total off-gas data to account for the local bias of any one fixed probe.
Which brings us squarely to reliability and data integrity. Even with great sensor placement, tech and human factors can introduce huge risks. What are the big technical risks?
Fouling and drift are the persistent enemies here. Critical sensors like DO and pH probes are really prone to fouling over long campaigns from a buildup of biomass, salts, antifoam.
The reading just slowly drifts off course, and anti-foam itself sounds like a necessary evil.
It is. You need it to prevent foam outs and contamination, but it's detrimental in two ways. First, it coats the sensor surface, slowing its response time. Second, and worse for the biology, antifoam increases bubble coalescence.
Explain that coalescence mechanism.
Antifoam molecules literally bridge the liquid film between two small gas bubbles. This stabilizes the film, causing the small, efficient bubbles to merge into larger, less efficient bubbles.
And that kills your surface area for oxygen transfer.
Severely reduces it. So you've managed the foam, but now your cells are oxygen limited because of it.
And beyond the hardware, there's the data governance, especially in regulated environments. We're talking about the ALCOA and ALCOA plus principles.
Correct. Attributable, legible, contemporaneous, original, accurate. Plus, complete, consistent, enduring, and available. In a modern facility, that means secure, validated historian systems, audit trails, everything.
For an engineer fighting with scale-up and variability, which of those principles is violated most often? Is it contemporaneous, where someone logs a result hours later?
It's often a combination of contemporaneous and attributable, and the sources were really clear on this. The integrity framework is so essential because what looks like biological variability is sometimes traced back not to the process, but to human errors.
That's a huge insight. You could spend a fortune trying to diagnose a biological problem when the root cause was an unlogged manual intervention or just bad sample metadata.
Exactly. Without ALCOA plus AG, you can't trust the data. And if you can't trust the data, you can't learn from it or improve anything.
So now that we have these reliable integrated signals, hard sensor data, validated by soft sensors, all secured by ALCOA+, how do they actually drive control?
Well, they deliver value when they translate into robust control actions that aren't just overreacting to noise. We see three key use cases. First is feed control. Soft sensors estimate uptake rates, allowing feed to be delivered precisely to maintain a desired growth rate.
Second, oxygen management. This seems like the most proactive use of the data we've discussed.
It really is. Using the OUR data, the system can predict an impending oxygen limitation before the DO actually drops. This lets you proactively adjust aeration or agitation. You're getting ahead of the problem.
And third, foam control, which is critical given its negative impact.
Right. Using advanced foam probes, the system can trigger extremely precise, minimal antifoam dosing. This cuts down on unnecessary additions and mitigates those mass transfer penalties we talked about.
So we're not just reacting, we're using the data for supervisory guidance. What are the guardrails on these control strategies? You don't want them making things worse.
No, you have to avoid reacting aggressively to noise. So you implement filters, deadbands, and often the soft sensor's output is used as supervisory guidance. It adjusts the set point rather than being the sole direct control input. Overly aggressive feedback can make the whole system oscillate violently.
This is where that high cell density E. coli example comes in. It seems to illustrate everything we've discussed, connecting analytics directly to a massive loss in yield.
It's a classic case study. At manufacturing scale, we're talking 20,000, maybe 50,000 liters. Delayed at-line glucose measurements caused that exact oscillatory feeding we talked about. The cells were repeatedly cycled into glucose excess and then limitation.
Wait, a 25% yield loss on a 50,000-liter run? That's not just a technical failure, that's a massive financial hit. Millions of dollars, potentially.
The sources emphasize that this timing error, which led to massive overflow metabolism and acetate production, resulted in a 15 to 25% reduction in final protein yield compared to the pilot plant. That's the difference between a profitable product and an economic failure.
So what was the soft sensor solution that fixed it?
They solved it by integrating the off-gas data. That allowed for tighter feed control to maintain an optimal growth rate, a mu of about 0.1 to 0.2, without the wild oscillations. Specifically, they used a rising RQ as the instant early warning sign of acetate formation.
So they could intervene and stop the problem before it even started to harm the culture.
Exactly. They preserved yields above 90% of the lab performance.
Beyond real-time control, what about the long-term value, process understanding, and scale translation?
Well, you can use multivariate analysis to mine historical batch data to find subtle patterns that precede failure. Things like a small but consistent increase in the variability of the DO controller output combined with slight shifts in the RQ trajectory.
Things you'd never see just looking at one batch.
Right. And for scale translation, it's vital. If overflow metabolites suddenly increase at the large scale, analytics are your diagnostic tool. They help you figure out if the cause is a hydrodynamic issue, real DO oscillations, or an instrumentation issue, like mistimed control actions. It lets you separate those two very different problems.
To bring this all together then, Process Analytical Technology, soft sensors, and rigorous data integrity, they really do form the indispensable nervous system of modern fermentation.
We've closed a lot of gaps, but challenges remain. We still need better ways to characterize that spatial heterogeneity from just a few sensors. And crucially, we need to translate these rich data streams into causal understanding, distinguishing correlation from causation.
That's going to require combining the physics of fluid dynamics with the cell biology data we're capturing.
And if we connect this to the bigger picture, success in the bioeconomy depends on combining all of it. Hydrodynamic insight, advanced sensors, soft sensing, and a really strong data integrity culture. It's the only way to reliably hit those tight yield targets.
So what does this all mean for you, the learner? Here is a final thought for you to chew on. The future success of industrial biotechnology depends on ensuring that our fermentation facilities can definitively close that gradient gap, moving beyond just measuring the process to truly understanding and predicting every cellular move before the cell even makes it.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Ernala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.